The third kind of factoring that we really should be familiar with is difference of squares. And a difference of squares is a very special case of factoring. And as we've started in all the other videos, we're going to start with an example of multiplying. 2x plus 3 times 2x minus 3. We'll multiply this out. 2x times 2x minus 3 plus 3 times 2x minus 3. We get 4x. I'm sorry, that should be 2x. So that's 4x squared minus 6x plus 6x minus 9. Combining like terms, those two terms cancel away. And so all I'm left with is 4x squared minus 9. This right here is an example of what's called a difference of squares, because that's literally what it is. It is a difference of things that are perfect squares. This is the same as 2x squared. This is 3 squared. So I could rewrite this as the square of 2x minus the square of 3. It is a difference of squares. Differences of squares like this are one of these special binomial multiplication patterns that you need to be able to recognize. There's a question on your homework about that. What are the 3 special general binomial multiplication patterns that you should be able to recognize? Well, this is one of them. The difference of squares. It essentially works like this. That a plus b times a minus b is always going to be equal to a squared minus b squared. You always will end up with this result. No matter what a and b actually are, if a is 2x and b is 3, then you'll end up with the square of 2x, which is 4x squared, and the square of 3, which is 9. And it's always minus. A sum of squares doesn't work out. I'll show you why. If I wanted to factor 4x squared plus 9, keep in mind that we can use splitting the middle on this, because after all, this is the same thing saying 4x squared plus 0x plus 9. 0x is just 0, and so sticking a 0x in the middle doesn't actually change anything. This means that now I'm looking for 2 numbers that add to 0 and multiply to 4 times 9 is 36. But here's the problem. 6 and 6 multiply to 36, but they add to 12. 9 and 4 multiply to 36, but they add to 13. In fact, there's no pair of numbers that multiply to 36 and add to 0. If that's the case, if you try to split the middle and there's no pair of numbers that work, then it's not factorable. You can't factor that polynomial. We can't factor this because there is no number that makes this work. But if this was 4x squared minus 9, giving me a minus 9 down there, and this was a negative 36, well now, negative 6 times 6 is negative 36, and negative 6 plus 6 is 0. And so that would work. 4x squared minus 6x plus 6x minus 9. Factoring by grouping, I take a 2x out, 2x minus 3. I can take a 3 out, 2x minus 3. And so that gives me 2x plus 3 times 2x minus 3. When you have splitting the middle, when you have a difference of squares like this, you could go through the process of splitting the middle. But you don't have to. Again, we have this pattern. If you see a thing that's a difference of squares like this, we can just factor it using this method. This makes factoring certain polynomials really, really easy to do. I'll give you another example. (98) x squared minus 50 y squared. Big numbers. Please don't try to do this by splitting the middle. You're going to end up with 98 times 50. It's a ridiculously huge number. Although you might also notice that 50 is not a perfect square. 98 you might be not as sure about, but no, it's not a perfect square either. Because what kind of factoring should we be looking for? Always, first, GCF. We can take a 2 out of both of those. And that's 2 outside of 49, x squared minus 25, y squared. And these you should recognize as perfect squares. On the left, we have the square of 7x. On the right, we have the square of 5y. And so, following this pattern, the 2 out in front stays there, but we end up with 7x plus 5y times 7x minus 5y. If you can get your polynomial such that you see a perfect square of the coefficients, and maybe there's not a coefficient, maybe it's just the number, or the variable, and then these are, of course, perfect squares of the letter x and the letter y, we can get this. Differences of squares can sometimes be a little disguised. I'll give you one more example so you can see this. 16x to the power of 8 minus 1. On the face of it, this might not look like a difference of squares. After all, 1 doesn't ring a bell as a perfect square, and certainly x to the 8 is not x to the 2. But if you think about it a little bit more, you realize that it actually is. After all, 1 is the square of 1. 1 squared is 1. Certainly 16 is the square of 4, but remember the exponent rules for powers and multiplying and things from previous units. That can be rewritten like this. If we have an x to the 4 inside a square, we would multiply the exponents to get that. And so now we do have a difference of squares. We have a 4x to the 4 plus 1, and a 4x to the 4 minus 1. But we're not done. This is also a difference of squares. This is not. That's a sum. We can't touch it. That's not going to go anywhere. But x to the 4, that's the square of x squared. So 4x to the 4 is a square of 2x squared. And so this factors again. 2x squared plus 1 times 2x squared minus 1. This is done. After all, 2 is not a perfect square. We can't square that. If this was another 4, if we had somehow worked it out so this was another 4 here, or if there was a 9 or a 16, then yeah, we can factor this again. The nice thing about 1 is that the square root of 1 is always 1. It doesn't matter how many times you do it. So we always end up with this particular pattern. So differences of squares are really useful, really quick ways to factor a two-term polynomial, because we always end up with those two terms. It's always that a squared minus b squared.